Right. So basically today we will talk about AC/DC bridges. So first of all, what a bridge is. So bridge basically uh, bridge is voltage divider and which redistributes the resistances, है ना, present in the circuit. So basically it simply changes how the voltages and resistances are behaving in a circuit. And if we find that this circuit or some resistance is unknown, what is the way by which we can ensure that or how to measure the value of a resistance? Okay, so let us just start with some bridges. So I will start with some basic theory. So a bridge circuit is a pair of two component voltage dividers connected across the same source. So this is the same source E is connected across, and here you can see that this is one path, this is another path, this one is another path. So since both of them are connected across this is the voltage source which is connected, so you can see that this one is a potential divider and some voltage, suppose A, develops here, VA. Similarly on this side I have another path. So in this path also you can see that since this is connected with the same VEE and ground, so this path will also redistribute the same voltage. Suppose, so this turns out to be VB. So if I say that this is R1, this is R2, R3 and R4, so I can say that how do I know this voltage? I will use a voltage divider circuit. If you want to understand it otherwise, say some current I is flowing, so this will divide in two paths, right? And if both the paths are having the same total resistance, right? So the currents will be divided by 2, right? And if this R1 and this R3, similarly R2 and R4 are similar or of the same nature, same ratio, right? So the voltage produced at VA and VB under the balance condition, they will be exactly same. So VA is equal to VB, and therefore if you connect a voltmeter over here, it will show you 0 voltage, right? So this was the basis to start with, that we have a Wheatstone bridge connected through like this, through a voltage source E. So we find that R1, R2, R3, R4. And if I place a voltmeter here, so I can say that this is VA and if this is VB. Okay, so to find out this voltage, I can do right. So here you can see that we have here you can see that we now, since it is the current which is getting divided, if they are the same ratios and if VC and VB are same, that means the voltage drop across A to C and voltage drop across A to B, they are equal. Okay, so how do I know how much is the voltage drop? So this is simply a voltage divider circuit, and therefore on this ABD path I can identify VAB as Rx by Rx plus R3 multiplied by the voltage supply E is VAB. So VAB is equal to VAC. So VAC is R1 by R1 plus R2 into E. Okay, so obviously E and E, they go off. So now you cross multiply, so you will get Rx into R1 plus R2 is equal to R1 into Rx plus R3. Okay, therefore open the bracket, you will find that you have R1 and Rx over here, R1 and Rx over here as well, and therefore what remains are these two. So Rx into R2 is equal to R2 into R1 into R3, giving you Rx. If Rx is unknown, if Rx is unknown and other three resistances are known, then there is a relation, right? So simply R1 into R3, the opposite branches are multiplied, divided by this branch is equal to the unknown value. Okay, so this is how a Wheatstone bridge is a highly sensitive mechanism by which you can very minutely, very precisely identify the value of an unknown resistance, right? So now the thing is, for example, if you take this circuit, if there is some voltage source, whatever, okay. So if this is unknown, you have the knowledge of these three resistances. Simply as per the derivation, you can apply and you will find that Rx is this. Now to know these, you must know their values accurately and precisely. Okay. Now here one important thing to consider or observe is that there is some wire resistance, right? How much might be the wire resistances or the contact resistances of the contacts, right? Because eventually it is some material with which it is soldered, right? And then there must be some resistance on the wire, right? So what do you think, how much might be the contact resistance and internal resistance of the wires used? Can anyone tell me how much might be the contact resistance or so? If I say that I have a contact at 1, 2, 3, 4, 5, 6, 7, 8. So in this Wheatstone bridge, I have 8 contact points. Now these contact points are having contact resistance. What is the usual magnitude of these contact resistances? Can anyone guess and tell? Anyone just unmute yourself and tell me. किसी से पूछें, किससे पूछें? Kunal, are you there? Kunal,
5 ohms or something.
5 ohms or something, right?
Yes, sir.
Okay. So if I say, chalo, let's take a closer estimate, say 1 ohm, right? So I have 8 contacts. So since this value is 750 ohms, so 750 plus 1 ohm on this side plus 1 ohm on this side. So chalo, this value has become 752 ohms, right? Similarly, other values. Therefore, if I make this one as 752, this one as 802, this one as 202, for example, if we are just taking it as a thumb rule, this value will still not change significantly, right? This is turning out to be, let me just see how much does it come. So still it is 300 ohms. Okay. So now the point is, when contact resistances are small and your considered resistances are high, it will not produce a major difference, and therefore we can still go ahead with this, right? However, now consider a situation when you want to measure very low resistances. For example, the unknown resistance is 1 ohm itself. So how will you measure a unknown value of an unknown resistor? By using a Wheatstone bridge. Because in Wheatstone bridge, if these values are high or moderately okay, in mid-range, kilo ohms kind of, right? At that time, this is all right. But suppose if I want to measure the value of an unknown resistance, which is of significantly low value, say suppose 1 by 10 ohm kind of, right? How would we measure this? So that was the challenge which was resolved by Kelvin bridge. So in the another circuit was Kelvin's bridge. It is also known as Kelvin's double bridge, right? And even sometimes in some countries it is known as Thomson bridge. It was invented by William Thomson, the first Baron Kelvin. Okay. This is used to measure very low resistances, typically less than 1 by 10 of an ohm, right? This is still similar to a Wheatstone bridge, or typically this is another variety of bridge, but it has some breakthrough arrangements. I mean, if I would say, if it is not equal to, if it is not as fine as E equal to mc square, okay, still you will find that this bridge is absolutely astonishing, very nice. So let us see how it goes and what they did and how he actually thought about it is of much interest. Okay, so let us check how Kelvin's bridge will work. And when I talk about Kelvin's bridge, we will have to check whether Kelvin's bridge will be able to measure very low resistances or not, and how it has handled the values of contact resistances. Before that, I should introduce you with a four terminal resistors. Four terminal resistors are low value resistances which come with four terminals, right? And these four terminals are such that they may have 1 ohm kind of resistance. However, these connect to the resistance very precisely. Okay, and what you have is four terminal resistance. So normally we have two terminals. In this case, we have four terminal resistances. Okay, such resistances are even commercially produced, so that is possible. If not, still one can go with the way we solder wire, because in this arrangement they have very precisely created low value resistances. So we have a four terminal resistance. So what we have normally is the standard Wheatstone bridge. So if I draw it in some other way, I'm making it easier so that we can rather more conveniently understand it. So now here I will place the voltmeter or galvanometer, right? And here I can say R1, R2, R3, R4, right? So now what I have is I can take R3, R4 to be high values. So maybe 1 kilo ohm range, right? However, say R2, I want to keep it very low. So obviously, if this one is low, the unknown should also be low, right? Because eventually this is the ratio by which we are dividing the voltage supply, right? So to distribute the voltages in the right ratio, you must have, if you are trying to measure a low voltage, low unknown resistance, you should have another known resistance of known and low value. Okay, now you see, if this is low and then over here you are adding some resistance, internal resistance, right? So what kind of resistances are getting introduced? So let us see. Just a minute, there is a call, huh? Okay, so we are seeing that what kind of resistances are getting added. So let us take things in a very straight fashion where we have the resistances. So this is a contact resistance. 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 Over here we have contact resistances, right? So when we have such contact resistances, say this was 1K plus 2 ohms, these two, say 800 ohms plus these two, so 2 ohms. Now suppose this one is 1 ohm, this one is also 1 ohm, added with plus 1 ohm, maybe say 0.5 ohm, 0.5 ohms. So what is happening is this is getting added. Since these values are getting added, this will create a difficulty for us. Observe it very closely that since on the top part say P and Q resistances, so P and Q, they are not getting affected significantly because the addendant is very small. However, in the low side, this is significant. Okay, so let's try to come up with what we can do. So Kelvin's bridge said, in Kelvin's double bridge, what he did was, let us introduce two more resistances. Okay, so with his suggestion, his innovation was to now make P and Q this way, and over here he said, okay, this is R and this is S as usual. Then he suggested that include one resistance like this, one resistance like this, and over here include it that way and add one more resistance here. And then he suggested that now here you place the voltmeter. Then he also said that let this be A and B and this be C, three resistances. And now this is this, right? So all of you might have studied star delta connection in electrical engineering course. Have you all studied star delta connection? This is called delta configuration, and it can be broken into this type of combination, right? So usually it is drawn this way. Right. So this value is this equivalent, right? This is calculated as AB by A plus B plus C. This one, this resistance, this equivalent resistance is AC by A plus B plus C. And this resistance is measured as BC by A plus B plus C. This is the delta connection. Okay, so if I can rearrange this star delta connection in equivalent star connection, right, which we will do theoretically only. Practically we have simply connected it this way. So what will happen in Kelvin's double bridge, when you will resolve it in that style, you will get this star connection, right? Which are equivalent resistances as we had discussed. So now you see, you had P, you had Q, you had R, you had S, right? Because of the insertion of those resistances, now you have AB by sigma A. This is your AC by sigma A. Sigma A is A plus B plus C. Sigma A is A plus B plus C. And on this side, this is BC by sigma A, right? So here you see that now this one is, here you see that this part and this part, now they are added together, right? So creating similar kind of bridge as Wheatstone did. However, in Wheatstone case, these were high values or middle values. In Wheatstone's case, in Kelvin's double bridge, he inserted one more bridge and then created this equivalent theory, right? And with that theory, he propounded that if now this is worked upon, so now you can see that as per this development or this theory, uh, so now with this development, now we can say that P by Q is equal to R plus AC by A plus B plus C divided by S plus BC by A plus B plus C, right? Now we can solve this. Once you will solve this, Acha, one more relation he had given to us was, in this circuit, he had said that P by Q must be of the same ratio of A by B. Okay, so this is identically equal to A by B as well. Okay, so with this relation, if I cross multiply and solve, so what will now, here only you can see that this B goes here, so this is ABC by ABC, ABC divided by A plus B plus C. Similarly, this part goes here, so this is ABC divided by A plus B plus C. So these two terms will go off. What will remain is, this will be RB is equal to SA, indicating that R by S is equal to A by B. Now, Kelvin has already said that P by Q, which are mid-value resistances, should have some ratio and the same ratio should be still with A by B, and these A and B resistances which have been connected separately, they are also mid-value resistances. So they will also be not affected by the contact resistances. R and S are the two resistances which are of low value, right? So we will see it further, how it develops. So as long as you are able to maintain the ratio of R by S and A by B, there will not be significant difference in the contact resistances. How? Let us check. As such, I have told you that with this relation, you can calculate the unknown value. If R was unknown, you can calculate. S is a low value. However, in this double bridge arrangement, the effects of contact resistances has gone off. So we will now check how in Kelvin's double bridge this relation has gone. Okay, so let's come to this. So what was our standard double bridge? Now he had said connect it like this, right? P, Q, R, S, A, B, C, right? And then this is connected like this. So let us check where would we find some significant contact resistance on this side. I should take some bright color. So this is the contact resistance. This is the contact resistance. This is the contact resistance. This is the contact resistance, right? This is where he said that instead of using two wire resistances, let's take 4 terminal resistances. So here he removed that part and came up with four terminal resistances. So now, rather than this, you will connect it like this, and rather than this, you will connect it. I am drawing it once again so that you can clearly see that what we are drawing is still the same. Okay, but now we have the 4 terminal bridge or 4 terminal resistors, especially for the low value ones. Right. So now can you see that with a 4 terminal system resistor, we have connected like this, right? Typically we have used 4 terminal resistance because these are low resistance and they are very difficult to measure. This resistance is actually 1 by 10 ohm, right? And this is what we want to identify how much the value is. So now you see how resistances have been merged. this resistance and this resistance, you see, this is coming in series with P. So if P is 800 ohms plus 1 ohm, it is insignificant. So if I number these terminals now and I take account of each contact, and number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Even, chalo, let's do 13, 14. Okay. So now you see that 1 and 2, 1, 2, and even this 5, these three resistances are coming in series with P. 1, 3, 5 are coming in series with P. However, P is much larger than 1, 3, 5, and therefore addition of that will not be affecting. Similarly, 3, 4, and 10, right? Q is much larger than 3, 4, 10, and that may be ignored, right? However, so these have gone. Regarding the source always have some internal resistance, so I can account the drop or internal resistance due to 7 and 12 may be included in the power supply. So that is also taken care of. Now on this side, A and B are mid-value resistances, right? So in that case, this 6 and 13 are in series with A is much greater than 6 and 7. Sorry, 6 and 13. So that will also go off. Similarly for B, B is much greater than 9 and 14. So that also has been taken care of. Now here this C is also a mid-value resistance, and therefore 8 and 10 contact resistance, they have also been taken care of, right? Therefore, with the derivation which we talked about, now we understand that A by B is equal to R by S. This is S, right? And with this relation, there is no effect of contact resistances, right? So a very low value can now be very accurately measured even in spite of the presence of 1 ohm, 5 ohm kind of contact resistances. In fact, in this part, even I had not talked about the resistance due to the wires. Still, which has this all has been taken care of. So therefore, just think how Kelvin might have thought about such a beautiful circuit which has amazing performance and can take account of all the contact resistances. Okay, so that was the beauty of Kelvin's double bridge, and this finishes our today's discussion. Okay, I hope this was clearly understood by you people. You can find much more material in the books as well as on blogs and websites on the internet. So do check it out. This is a very interesting thing with the consideration of conversion of delta to star structure. You can very conveniently analyze it. Okay. So this is what we had to talk about, right? And here you can also see that basically what was C, you might have observed that basically this was on one side, it was on one side, you see this is AC by sigma A, on this side BC by sigma A, right? So if I talk about the ratio of it, right, you can see that if I talk about these two resistances, these two have been, the C has been distributed in a ratio which is AC by sigma A divided by BC by sigma A. So everything goes off. What remains is A by B. So what it redistributed? It redistributed this C, right? So C has been redistributed in the ratio of A to B. And therefore the effect of C has also been nullified. So this is an interesting question. People can ask how C has been redistributed. So in one way, you can say that this is a resistor divider bridge, okay, which divides the resistance uniformly so that its effect does not come in the calculation of resistances, right? So once again, I will just quickly repeat so that the recording is complete. So far we had been talking about DC bridges because DC bridges were good enough to help us calculate or measure mid-value resistance measurements, or in fact we had Kelvin's double bridge which helped us measure even low value resistances. Okay, the difficulty was that these knowns and unknown values were purely resistive, right? So there was no question of impedance consideration. In case of AC bridges, now we feed alternating frequency, and because of which impedances come into picture. And since impedances are there in the picture, we can in fact work with unknown inductance, unknown capacitance, lossy inductance, lossy capacitors, right? So this is a rather more practical situation where we want to work. Okay, so right. So eventually, when we are talking about bridges, everything is going to be typically like your standard Wheatstone bridge, right? So once again, I can draw the same Wheatstone bridge, but now this time I will draw them like standard impedances, right? And this will be fed with alternating signal, right? And now you have Z1, Z2, Z3 and Z4. Obviously, since on these two parts you are feeding the signal. Okay, one more thing, if I ground this, so this becomes the zero reference. So over here these are the two values which you can consider to measure, so V1 and V2, right? So your detector will be placed somewhere here, right? So this is the standard thing, and suppose this is the input signal Vs, so this voltage is at V, right? Alternating signal. So if we have this kind of bridge, what is the condition of balance? So let us consider what the balance condition will be. So the condition for balance, as usual, Z1 by Z2 is equal to Z3 by Z4. So I can write Z1 by Z2 is equal to Z3 by Z4, right? Directly taken from your Wheatstone bridge. Okay, so this should be so both in terms of magnitude and phase, right? So this is the beauty of AC bridges, that not only, since these are impedances and we are feeding alternating signal, some high frequency signal, so naturally magnitude and phase, both of them will come into picture. Okay, so what is the voltage at V1? So V1 I can write as Z3 by Z1 plus Z3 multiplied by power supplied. So this is V, right? And similarly, I can write for V2 is equal to V2, this one. So V2 will be Z4 by Z2 plus Z4 multiplied by V, right? A standard voltage divider theorem. So this will give you this value. Okay, so this implies that so this simply means that your okay, so I can write Z3 by Z1 plus Z3 is equal to Z4 by Z2 plus Z4, right? And while I solve, I can just in fact invert it. So if I invert, I can write it as Z1 plus Z3 by Z3 is equal to Z2 plus Z4 by Z4. So now when it goes inside, so Z1, Z3 and Z3 cancel up, Z4 and Z4 they become this, and therefore this part becomes 1 plus Z1 by Z3 is equal to 1 plus Z2 by Z4, and these 1 and 1 cancel out. So what you get is, this is what you got. Z1 by Z3 is equal to Z2 by Z4, right? So so wherever now we have Z1 by Z3 is equal to Z2 by Z4, right? So this thing I will call as the ratio form, right, of the balance. So of course, this is Z1 magnitude angle theta1 divided by magnitude Z3 angle theta3 is equal to magnitude Z2 angle theta2 divided by magnitude Z4 angle theta4, right? So if it is so, I can say that magnitude of Z1 by magnitude of Z3 should be equal to Z2 by magnitude of Z4 under the balance condition. Similarly, your angle theta 1 minus angle theta 3 should be equal to angle theta 2 minus angle theta 4, right? So this is how we work with, or you can even so no, no, where you had these things, your impedances are like this, right? Z1, Z2, Z3, Z4. So now you can see that theta 1, theta. So this is theta 1 and your theta 3. If you subtract these two, and this is theta 2 and theta 4. So difference between these two consecutive arms, the phasor angle should be equal. Okay. You can also write it like angle theta 1 plus angle theta 4 is equal to angle theta 2 plus angle theta 3. So what you find is sum of these two angles and sum of these two angles should be equal, right? So in this way, we get both the types of combinations. If you subtract, that can also work. If you add between the opposite branches, that will also work. Similarly, over here you can see that Z1 and Z4. So on one side you can add the angles of opposite arms. They should be equal, sum of the angles. And similarly, it can also be written as mod Z1 multiplied by mod Z4 is equal to mod Z2 multiplied by mod Z3, right? So in this way, if you multiply the magnitudes of opposite arms, that should also be equal. Okay. So this is the balance condition which we need to talk about. Okay. So this is known as product form of the bridge, right? So let me give you one example and tell me if this bridge will work or not. This is a bridge, right? Onwards, I will stop actually drawing this part and the detector because this is not required. Understand that this is already powered up and the detector has been connected and therefore it is fully functional, right? Otherwise, you can just skip it. So can you quickly analyze and let me know whether it will work or not? Can you create a balance condition? Just think about it and let me know. I can call it L3, I can call it C4, right? So, what is the possibility? Anyone, can you think of whether can I balance this bridge or not? Anyone? एनी से ही पूछ लेते हैं. एनी, आर यू समवेयर?
Yes, sir.
हाँ, can we balance this bridge?
Yes, sir. When R2 by R1 is equals to 1 by 1, means ratio of R2 by R1 and impedances and capacitance and capacitor and what
Right.
is this? Impedance means those ratio will be equal, then this will be balanced.
So can we get proper balance? Null condition, would we ever arrive at balance condition? Let us just see. This is angle.
Yes.
Yeah, who is speaking?
फेज डिफरेंस आ जाता है सर एल और सी के अक्रॉस सर.
सो
शायद अचीव नहीं हो पाएगा सर, वो कैंसिल आउट नहीं कर पाएंगे R1 R2.
दिस इज द पॉइंट कि ये तो 0 डिग्रीज है, राइट? सो दीज एंगल्स आर 0 डिग्रीज. Now on this side this is plus 90 degree and on this side this is minus 90 degree, right? So the condition of balance, if I say opposite angles, sum of the opposite angles should be equal. So on one side, if I add angle R1 plus angle R4, right? So ये हो गया तुम्हारा 0 डिग्री minus 90 degree, right? And this must be equal to another angle 0 degree plus another angle plus 90 degree, which is equal to 0 degree plus 90 degree, right? So now you can understand that by any means these two are not going to help us. Okay, so it is not always necessary that the bridges will balance. Okay, so one has to think about various conditions when I can understand that yes, okay, this will balance. Okay, so basically in a bridge you will find that there is one thing which is, say, unknown. So then the other three branches, arms should be known, right? Interestingly, you can place your unknown measurand at any place on any arm, but the condition is that it should be the other arm should be known. Okay, so this is the primary idea of bridges. So let us consider some situation when let us take some situation when if a capacitance is absolutely pure. So we want to measure pure unknown capacitor, right? So how to measure it? So okay, we have 4 arms. I can place my measurand anywhere. So let me choose this. So this is CX, right? So in this case, as I can see that this is Z1, this is Z2, this is Z3, this is Z4. So as usual, what we do, Z1 by Z2 is equal to Z3 by Z4. So this may be wonderful if I make it resistive. So Z3 and Z4, both of them let be R3 and R4. So I have chosen this to be R3 and this to be R4, right? Whereas on this Z1 by Z2, you see there is a capacitor. Z2 is a capacitor. So if I will place another capacitor, which is a variable capacitor, measurable and known capacitor, so what will happen? Now I will receive a situation when this angle will get subtracted by this. This is purely resistive, right? So I can certainly arrive at a condition of balance, that is, if I simply consider this, so it will be 1 by j omega c1 divided by 1 by j omega cx, which is unknown, is equal to R3 by R4, right? So in this way, now j omega go off, cx come up, so cx is equal to c1 multiplied by R3 by R4. So now you understand that this part is a constant, right? So this constant simply got multiplied by the known capacitance, and under the balance condition, I can now calculate the unknown capacitance, right? So bridges are beautiful in a sense that AC bridges can help you measure unknown inductance and unknown capacitance, right? So let's go ahead with this. So the idea is you should be able to design a bridge in such a way that the bridge is balanceable and has known values. Okay, so let's consider another situation. I have a lossy capacitor. Right, and I want to measure the unknown capacitance, right? And I want to measure its respective real part as well as imaginary part. So how do I do this? Can you think about it? So first of all, as usual, let me place my unknown variable somewhere across some arm. So now I have Cx and Rx, which I don't know. So now what to do? If I place resistances across this, once again, this part of the ratio will not match with this part of this, and therefore it will create a difficulty for us. So purely resistive branches cannot be taken. Perfect. So what to do? Let us consider a situation when I can take something which is similar. So let me take another capacitor of known value and another resistance. So I have taken another thing which is symmetric, and on this side I can take simply resistive. So R3 and R4 are this, and this is Z1. Okay. So now what will happen? So in this case, now angles can be compared and equated. This part will become a constant, so we can very conveniently create an expression for measurement of Cx from the imaginary component of the equations, whereas Rx from the real component. Okay, so this is how we work. Is it clear? So in fact, if I equate it, so then I can write 1 by R1 in terms of admittance, right, plus j omega C1 equal to sorry, multiplied by R3 is equal to 1 by Rx. Sometimes working with admittance helps. So plus j omega Cx multiplied by R4, right? So now we can simply equate the real part and imaginary part. Okay, so if I equate the imaginary part, what you will get? J omega C1 R3 is equal to J omega Cx R4. So Cx is equal to, so j omega cancel out. So Cx is equal to R4 by R3 multiplied by C1, right? So this is from where we got it. Similarly, R3 by R1, okay, will be equal to R4 by Rx. So Rx is your R4 by R1 into R3, right? So we wanted to know what is Cx and Rx, unknown capacitance and resistance. So this is how we can measure this part. Okay. So the primary idea is how to create a bridge in a way so that my calculations would be easier and straightforward. Okay, so technically speaking, generally there will be variety of bridges. People come up with Wheatstone bridge, double the Kelvin's double bridge, in fact Maxwell bridge, Hayes bridge, and many more variety. But as a thumb rule, in fact, we need to consider a balancing condition. How and what variety of simple bridge will help me do straightforward calculations, and based on that, gradually we will come up to see what different bridges are. So basic theory of bridges is simply this. Okay, so this was first to be understood well, and then we can think of varieties. Okay, so we can either have a ratio bridge or a product bridge. So we have two different types of bridges generally by way of calculations, and what that is, so one is your product bridge and other is your ratio bridge, right? This is the kind of calculation. So when you are working with impedances, you are basically working with ratio bridges. If you are working with admittances, right, so product bridge would be rather easier to work with. What these are? So I can consider once again a similar type of bridge. Other things have been considered that this has been powered up properly. So we have Z1, Z2, Z3, Z4, right? So this is the ratio, and suppose this is unknown. So you can write Z2 is equal to Z1 multiplied by Z4 by Z3. Z1 by Z2, Z1 by Z2 is equal to Z3 by Z4, right? So Z2 is equal to Z1 multiplied by Z4 by Z3. Okay. So this is the condition of balance. So generally what we will do, so generally what I would prefer that this part, this is R4 by R3 is equal to some constant. So this part will become a constant, will become a simple multiplicative factor for Z1, right? Since Z1 is known and we are multiplying a constant, so calculation for Z2 will be straightforward, right? So this is why this type of calculations working with impedances in this fashion, this is understood as a product bridge. Okay, so this is how we get very good and straightforward solution. If you come for the product bridge, so in case of product bridges, is still you will have the same thing. So in case of product bridges, we will work with admittances. So Y1, Y2, Y3, Y4, which is equal to 1 by Z1, 1 by Z2, 1 by Z4, and 1 by Z3. So what happens is, since we are working with admittances, it would be sometimes easier to in fact do the multiplications and other things. For example, in this case, what you will get is Z2 is equal to Z1 multiplied by Z4 by Z3 as usual, right? So regarding the Z3, since so this was Z1 into Z4 multiplied by 1 by Z3. 1 by Z3 is basically Y3. So this becomes Y3, Z1, Z4, right? So now Z1 and Z4 are purely real, right? So they become equal to a constant, and this constant gets multiplied by the admittance of Y3. Okay, and this is equal to your Y2, right? And this is how this becomes or turns out to be very easy. Simply to multiply the real component with the constant, angle component with the constant, right? So we have ratio bridges, we have product bridges, right? Both the types of bridges we use. Okay. So now we can take few examples which will make it clear. Okay, so let's consider a situation when you want to measure a lossy inductor. You want to measure lossy inductance, right? So how would you measure lossy inductance? So as usual, we will create a bridge. We have created a bridge. I have to insert my unknown part somewhere. So let me choose this to be here. So let me insert my inductance and resistance here. So this is Lx and Rx, right? So to balance it out, since we create ratios of the things, it would be interesting if I can choose inductor and resistance. So now these are variable inductance. So this is L1 and R1, right? On this side, I can take R3, a resistive one. On this side, I can take R4. These are also variable, so I can create the condition of balance, right? So when I create the condition for balance, right? So what to do? Let's write the condition of balance. So you can simply take this from this product bridge, okay? And because we have already derived it, so you can simply reach here and write Z2 is equal to Z1 multiplied by Z4 by Z3, okay? So your Z2, this is Z2, right? So Z2 will become equal to, so J omega Lx plus Rx is equal to Z1, right? So this will be, so if you, so Z1 is, what Z1 is? J omega L1 plus R1 multiplied by, since we have taken purely resistive known arms, so this is R4 by R3, R4 by R3, and which is a constant, right? So it can simply be multiplied inside, and what you will get is, so this gives you J omega Lx is equal to J omega L1 multiplied by R4 by R3. So these two cancel out. So what you are getting is Lx is equal to L1 multiplied by R4 by R3, which is a constant. So in this way, with respect to a known inductance, you are able to calculate the unknown inductance, right? Similarly, for the same situation, what your Rx will be? So Rx will be equal to R1 multiplied by R4 by R3, right? So in this way, you can see that you are able to measure unknown resistance, the real component of the unknown impedance, as well as the imaginary component of the unknown impedance, right? So this is the beauty of bridges with which we can work, correct? So if we have been able to do this, can we do something for a lossy inductor? But suppose I do not have, so okay, let me take a situation when I have once again inductor, a lossy inductor, so Lx and Rx, right? Unknown lossy inductor. Okay, now I want to measure it using some bridge. So what kind of bridge? So as always, I will start with creating something where I can just consider where to insert what. Okay, so while I want to insert something on this side, obviously I will have to insert my unknown, so Lx and Rx, and the condition is that we do not have a known variable lossy inductor. So like in previous case, we had placed lossy known inductor on the in place of at Z1, right? This is Z1. So at this location, we had placed lossy inductor, which was known to us, and the Z3 and Z4, we had made them purely resistive so that they can simply become a constant and get multiplied. Okay, but in this case, what is going to happen? Since I do not have a lossy inductor, I cannot place it here. Okay, so still to do the honors, what we can do, I can place a resistance here, place a resistance here, right? So Z1 and Z4 are resistive, and at Z3 I can place a known lossy capacitor, right? So now since I have a known lossy capacitor, I can now try to balance, because you know this one will go towards negative 90 degree, this will go towards positive 90 degrees. So somewhere between positive negative 0 to plus 90, over here 0 to minus 90, when they will cancel each other, right, we will arrive at some situation when we can actually equate and get the condition of balance. So what would that be? As usual, Z2 multiplied by Z3 is equal to Z1 multiplied by Z4. Okay, so opposite arms, multiplication of opposite arms should be equal to multiplication of other opposite arms. So it's equal to Z1, Z4. Okay, so now we can write that Rx plus j omega Lx is equal to, now here I can take the admittance form. So now here you see Z1 and Z4, they have been considered to be resistive. So I will take R1, R4 multiplied by, now this Z3 will come down, right? So 1 by Z3, I can write it Y3. 1 by Z3 is equal to Y3, right? So I can write it in the form of admittance, and this will become 1 by R3 plus j omega C4. Sorry, not C4, C3, right? So now we open it. So now you equate Rx is equal to R1, R4 by R3. So this gives us one value of unknown. The other unknown is j omega Lx is equal to j omega C3 multiplied by R1 R4, right? So j omega and j omega cancel out. So Lx is equal to, so unknown inductance is equal to known capacitance multiplied by R1 and R4. Correct? So this is how we come to the conclusion of today's discussion, that bridges are useful to measure impedances. And while I measure impedances, I have to design the bridge in such a way that in which what kind of component we have to include in unknown arms of a bridge, so that whatever unknown values we have to calculate, this calculation will be easy and straightforward. Okay, so go through the reference books, try to do some examples and questions in bridges, and see how different arms are designed, what kind of calculations are done. Typically, talking about a specific bridge will come into picture when we will face a difficulty, right? For example, yesterday we used Kelvin's double bridge because we were not able to account for the contact loss or contact resistances, right? And the unknown value of resistance was in the range of 1/10 of few ohms, right? So that was the specialized bridge. So this is how we will, in fact, consider variety of AC bridges in our subsequent classes. But the prime idea was, think about a bridge which can help us calculate. Okay. Correct. So so far we had been talking about variety of bridges, and regarding the bridges, the key advantage or requirement of bridges is to be able to measure certain parameters like inductance, capacitance, resistance. If we talk about typically only the resistive component, DC bridges will work, and if we have to take for the do the measurement of inductance, capacitance, or impedances, AC bridges are required, right? So AC bridges are typically required for measurement of impedances, and in fact, since this impedance measurement will be based on resonance, so frequency will also come into picture. So if frequency comes into picture, obviously, if you have known parametric values, you can even identify some unknown frequency. So for the sake of frequency measurement, AC bridges are also used. So today we will see some more bridges. We have already seen Hayes bridge, Maxwell bridges in last class, right? So let us go further into this. Technically speaking, whether there are different types of bridges or not, eventually the Wheatstone principle will be there, where we talk about the ratio or product of some various arms involved into the things, right? So let us go ahead with what we have been talking about. I will share the PPT. Right. So today we will talk about some other bridges. To start with, let's talk about the Wien bridge, right? So we will talk about Wien bridge, right? So what Wien bridge is, So I can simply draw it this way. On one arm, I will have this. On other arm, I will have resistance and capacitance, and then on the rest of the two arms, I will have typically this. So I can write these as R1, C1, R2, C2, R3, C3. Oh, sorry. R3 and R4, right? So how do we measure or obtain the balance equation? Right. So as usual, we have, if I consider it as Z1, Z2, Z3, Z4, right? So I can write it as Z1 by Z2 is equal to Z3 by Z4, right? So I can obtain the ratios, right? So can we write the actual values for this? So this will turn out to be regarding the Z1 component. So Z1 will be, since R1 plus j omega C1 divided by in fact, let's take Z4 here and Z2 here, so I can simply write it Z4 is R4, so this will become this. This will be equal to from this side Z2 and Z3 is already R3, so it will go here, R3 multiplied by, now this is a parallel combination of R2 and C2, so this will be R2 by j omega C2 divided by R2 plus 1 by j omega C2, right? So this we can solve further. So you will get R1 plus 1 by j omega C1 multiplied by R2 plus 1 by j omega C2 multiplied by R4 is equal to R2 R3 divided by j omega C2, right? This can further be opened, and once you will open it, you will find that this is J and this is J. So when these two will be multiplied, so square root of -1 multiplied by square root of -1 will come out to be -1, right? So these two terms will become minus, so I will solve it as R1 R2 minus 1 by omega square C1 C2 plus R2 by j omega C1 plus R1 by j omega C2 whole multiplied by R4 will be equal to R2 R3 by j omega C2, right? So now with this equation, we can compare the imaginary component as well as the real component, right? So with the imaginary component, what will you get? So on the imaginary component, this part is there. So you will get R2 R4 by C1 is equal to R2 R4 by C1 plus R1 R4 by C2 is equal to R2 R3 by C2, right? So this forms one condition for balance, right? So this is first condition using which you can measure the unknown capacitance, right? While R2, R4 and C1, these are known, and this is your unknown. So you can solve it for this. Okay. Then we come to the real part of it. So you will find R1 R2 minus 1 by omega square C1 C2 multiplied by R4 is equal to 0, because on the right hand side there was no real component, right? So this is equal to 0. So I can write it as R1 R2 is equal to 1 by omega square C1 C2, which in turn converts to be omega is equal to square root of R1 R2 C1 C2, right? So now you see in one part where C2 was unknown, that was all right, we can measure it if we know the frequency of operation, right? So if this is known, and suppose if it is known C1 C2 R1 R2 and there is some unknown frequency to be measured, so you will find the condition of null balance and based on that null balance, whenever this null balance comes, accordingly you can identify that. So you can keep on varying the frequency and check when does the null comes. So based on this C1 C2 R1 R2 values, you can calculate or identify the precise frequency which is unknown, right? So that is the advantage of Wien bridge. Okay, so that was one thing. Okay, so technically speaking, you have 4 arms, you have some frequency, then you have to work on for the balance equation. Whatever is the balance equation, usually you have to find, you will get it by way of practice, whether what frequencies, what arms should be resistive or should carry impedance, so that solving of the equation becomes easy, right? So let us take one more bridge, which is known as Anderson's bridge. Anderson's bridge, right? This is an interesting bridge, and we will try to see how this is solved. Actually, solving the bridges is the art, and usually it comes by experience. So more practice you have will give you a better physical insight. So you see here we have R1, say suppose this is unknown, so rather than R2, now we have written LXRX, right? Then this one is R4. On this side, what they have done is there is one arm, there is another arm, there is another arm, right? And then over here they have placed the detector. So let us call it to be R3, C3 and R5, right? And as usual, this is where your supply has been connected, right? So can anyone suggest me how to solve this or how to arrive at the balance condition? Can anyone just intuitively suggest how to analyze this? Anyone? Ishita? Ishita, are you there?
Yes, yes, sir.
How would we solve this? How to handle this weird looking bridge? We have to obtain the balance condition, right? So what we will do is, let us now can you see that this is a delta? So this is a delta, right? So if I understand it as R1, R2 and R3, so this can be broken into a star, right? So this is called delta to star conversion. This is a very important conversion and you might have done it in electrical networks theory. So value of this arm will be R1 R2 by R1 plus R2 plus R3, right? Similarly, this one will be, Ishita, can you tell me what this would be? This arm, as we did for this branch, the upper branch, it was R1 R2 by sigma R. Similarly for R3, what it would be?
R1, R3,
R1 R3 by sigma R, right? And similarly, this one will become R2 R3 by sigma R, right? Sigma R is R1 plus R2 plus R3, right? The bridges are typically mathematical solving problems. So eventually you have to solve and handle with the equations. So now you see what it will become. You have this, this and this. So accordingly you will have three arms, right? I can call it as ZA, ZB, ZC, right? So now since we have understood how to identify what will be the arms, so can we write ZA? ZA will be R3 into R5, R3, R5 divided by sigma R. So what is sigma R? Sigma R will be R3 plus R5 plus X3, XC3. So XC3 is 1 by J omega C3, correct? Similarly, you can write for ZB. ZB will be R3 into 1 by j omega C3 divided by the same value. So R3 plus R5 plus 1 by j omega C3. And similarly, you will have ZC. ZC is these two divided by this. So this will be R5 into 1 by j omega C3 divided by R3 plus R5 plus 1 by j omega C3. Correct. So in this way, we can find the equivalence. And once you have found the equivalent, what you will get? You will get it as ZA, ZC, ZB like this, and this comes down, so R4, and ZB is connected with the detector, right? So once we have got this, now you see here you had R1, you have LX, RX, ZA, ZC, ZB, and R4, right? So I can redraw this bridge. Now you see, observe here. Now R1 and ZA are in series. ZC is another arm. R4 is another arm, and one more arm is LXRX. And over here you can see that ZB and D, they have become in series. So I can understand that ZB is basically internal resistance of the detector or the galvanometer which we have placed for null detection. So accordingly, in this bridge, ZB will go off. I mean, we can ignore ZB or we can consider ZB to be an integral part of D, right? So our new bridge will become this. This so here you will connect it with ZA and R1. On this side you will connect on this side you will connect ZC, and on this side you will connect R4, right? And this is your ZB connected with your detector D, right? So now you see this has become a simpler expression, a simpler equation, simpler bridge with no more complexity. We had a complexity level of this, which we have reduced down to a simplified bridge. Now we know the values of ZA, ZC, so and your LX, RX, and other values are now known. So now we can write the expression. So what will be the balanced the equation for the balance? This will be R1 plus ZA divided by ZC is equal to your Rx plus j omega Lx divided by R4, right? ZB has been considered to be the integral component of your detector, and therefore it will not make any difference. So now since we have these values, now you can resolve and compare the real part and imaginary part and solve this. So you can take it as a homework and just try to solve the equation. This is simply solving the equations. Okay. So we saw that this was one good way by which we could do it. I can redraw this. Right? So we had R1, LX, RX, R4, then let me write it as R3, C3, and R5. Okay. So one way was to break this, right? If I don't want to do that, is there any alternative way? So I can now talk about star to delta conversion. Earlier we did delta to star. Now we are thinking of converting it from star to delta. And where is your so what is your star? Star is if I have R1, R2, R3, then I can create equivalent delta, right? And in case of delta, this value will be equal to this will be R1, R2 plus R2, R3 plus R3, R1 divided by the opposite arm, which is R2. Similarly, for this branch, what will be this value? Who will tell me? Dinesh? What would be this arm?
Or the one on the left, sir?
Yeah, this one. For this one, what will be this arm? This arm will be multiple, as usual, the numerator is same. So I will write it as sigma R1, R2, right? So it is understood, divided by the opposite arm, which is R3, right? Similarly, for this will be sigma R1, R2 divided by the opposite arm, which is R1, right? So that was the star to delta conversion, right? This is the formula. Now here, can you see a star anywhere, somewhere? Dinesh, are you seeing some star somewhere in this circuit? One arm, another arm, one more arm, right? Yes. So in this way, there is one single node with which three resistances are connected. So accordingly, your delta conversion will be one arm will become this to this, another arm will become this to this, and one more arm will become across this, right? For example, can you tell me what will be this value? This will be sigma R1, R3, R5. I mean, involving sum of R1, R3 plus R3, R5 plus R5, R1, right? Divided by the one arm which is not connected. So R1, R5 are already over here. So opposite one is the left one is R3, right? Similarly for this one, you can write the value. So this value will be the upper sigma divided by R1, R3, R5, and take two at a time, divided by, now R1 is left, so R1. And similarly for this one, you will get the value sigma R1, R3, R5, take two at a time, and R1, R3 are involved, R5 is opposite, so this will be divided by R5, right? So if I convert these three arms into equivalent delta, right? So then let us see what do we get. So we will get it as I have in LX, RX as usual. I will have R4 as usual. I will have the detector as usual. I will have a capacitor as usual, right? Now for the remaining three, we created the equivalent, right? So I can connect it or show it like this so that we are rather more clear. So this is ZAB. This one will become ZBC, and this one will become ZAC, right? The way we did, right? We can in fact write it as A, B, C. So that was the notation. So this is how AC, AB, and BC, they have been written, AB, BC, and AC. Now, how about the power supply? The power supply has been already made like this, right? So now here you can see that with respect to the source, rather when it is AC, we write it as V is small. So this is VS. So VS is in parallel with ZAC. So I can consider this whole thing as an integral part of the power supply itself, because eventually it is the voltage which will appear across this, right? And therefore I can ignore this ZAC. In earlier case we had ignored something. In this equivalent also we got some clear justification about how to ignore why we can ignore ZAC. So now what remains? So now what we get is, now we have ZAB. On this arm we have LX, RX, LX, RX, and on this side we have a capacitor in parallel with ZBC, so they are connected, and then the fourth arm is your R4, right? And here you see that the detector has been placed, right? So now, and this is the power supply which is connected as usual. So now you see, in some earlier case we had seen, acha, And what were these? ZAB, BC, and ZAC. They were formed out of R1, R2, R3, three resistances, right? The three resistances were R1, R3, and R5. So accordingly, this value will be purely resistive, right? And so this is equal to ZAB. And what is ZAB? ZAB is sigma R by R5. So this is sigma R by R5, right? So this is again purely resistive. On the opposite arm, this is purely resistive. Now over here, this is inductance and resistance. This is capacitance and resistance, right? So these two arms will help us do the things, and therefore now we can proceed to solve the equivalent things. So I can in fact create a ratio. I can create a ratio of this versus this, and this versus this. So I can write so now we have this thing. So I can write its equivalent equation for balance is ZAB divided by ZBC in parallel with the capacitance. So 1 by J omega C3 is equal to this one. So this one is Rx plus J omega Lx divided by R4, right? So now we have typical values for different combinations. So you can simply write it as ZAB into R4 is equal to these two components, this and this. These two come here, right? So if I solve it properly and compare the real and imaginary component, you will find Rx. Let me write the simplified component directly. Or okay, it's better if I write the right expression. So RAB into R4 multiplied by 1 by RBC plus J omega C3 is equal to J omega Lx plus Rx, right? So with this, I can now compare. So Rx is equal to RAB R4 by RBC, right? And you see RAB and RBC. So both of these had numerator common, so that will cancel off. And what remains is equal to R1 by R5 into R4 is equal to Rx, and therefore now this is your one unknown. So resistive component now we have measured, calculated correctly. Similarly, regarding the Lx, it will be RAB R4 C3, right? So once again, you substitute it with the actual value. So what you will get is Lx is equal to sigma R right? R1, R3, R5, I mean take 2 at a time, divided by R5 multiplied by R4 C3. So this is another expression for calculating Lx. So unknown resistive component, unknown inductive components we have been able to calculate. So in this way, we finish the part of bridges where we wanted to cover something special, right? So now we understand, we have read about 4 or 5 different varieties of bridges, right? And I understand that all of these bridges were more or less similar to the standard uh, analysis of arms of a Wheatstone bridge. So all you need is to obtain the balance condition equation for balance. Usually prefer to have the ratios of resistive versus impedance components so that they cancel each other and create equivalent real and imaginary components which you can compare conveniently, right?